Alright, hope everybody has watched the video I shared the other day for your first homework assignment. If you haven't watched that, just pause this and watch that one. I wanted you guys to get an overview of acids and bases and kind of what's going on there to give you a lay of the land. And now I want to talk through 11.2. Very quickly, let me tell you, in 11.1, it'll probably go along with your homework, that if you haven't done that, make sure you get it done. Don't wait till Monday night. You're going to have too much to do. You know you will. So just go ahead and do it. Set yourself a goal and get her done. We'll probably have some of these. I'll try to give you guys a list of what we'll need. Maybe some general things. I will let you know what you need to know from these. We're not going to do a whole lot of memorization. We're pretty much out of time for that kind of thing. And I also personally happen to feel that it's not particularly useful to force you guys to memorize that at this point. I think it would be useful for you to have to memorize them for your college chemistry course, and be useful to be able to be flexible with those, but not really right now. So we're not going to spend a whole lot of time on any of these either. We're just not. But what I do want you guys to know, you do need to know a couple of things. We've got carboxylic acids. Look at those. They contain the COOH, like acetic acid. This is such a foundational deal. The COOH thing is, and you'll see it if you're kind of in any biology class or chemistry class in the future. Let alone if you're in organic chemistry, you'll really be familiar with them. Oxyacids. One or more oxygen atoms, one or more hydrogen atoms, and at least one other element, usually a nonmetal. You see what they are right here. And then we have binary acids right here. Okay, so you do need to know those categories. Okay. All right. So with that. I basically exempted a lot of 11.1, but not all of it, so be aware that that's going on. And you probably also will need to know these properties. So the things you ended up doing in your homework is what you need to know. So you need to know properties of acids, and then I'm sorry, this is actually the basis page, but the properties of acids and bases. You just need to know those things right there. Okay, you need to know they're corrosive, but they're both corrosive. They generally have a sour taste. That's not too hard to remember because lemons have got citric acid in them. They react with bases to produce a salt and water. They form ions. Acids that do are electrolytes. They cause a change in a pH. That's all kind of middle school stuff, so you shouldn't have too much of a problem with that. But then also look through your bases, that typically they are bitter. Soap is a base there, and they react with acids to produce a salt and water. So a lot of those are the same, the mirror image of the acid characteristics. So that shouldn't be too hard. But there's definitely going to be some fill in the blank, short answer, something like that. All right, so we're going to talk about acid-base theories. And I'm going to give you kind of the down and dirty for what we need to know for these, because what we're going to do is we're going to talk about acid and base theories, and then we're going to go on to actually talk about how to calculate pH and all that stuff. Some of that stuff was mentioned in the video that crazy dude did. And he kind of gave you the basic, the negative log of the concentration of H+ ions is pH. Okay, there's going to be a lot of this going on. Okay, so hopefully I can get you comfortable with the calculation, but it's really not that complicated because your calculator mostly does most of it. So you just need to remember that this is concentration and that it's in, I believe it's in moles per liter. We'll get there, but I just want you guys to know that we're not going to get super into applying a lot of these, but you do need to be familiar with them because they interact different ways. Okay, and so we're going to talk about the Arrhenius acids and bases. Then we're going to talk about the Bronsted-Lowry acids and bases. I think there's like an oh, that's what it is. It's got a little cross to the O there. Bronsted-Lowry, and then we have Lewis. All right, and so to be honest, I have never understood acids and bases on a very kind of like deep level. I don't really understand why they're a separate set of things and why they're not just treated like as another chemical reaction. But I guess it's to talk about a class of thing that all sort of shares a property. They all react this way with metals. They all do this with acids, do this with bases. You always get a salt, out of them. So just very quickly, I want this to be sort of a 20-minute video because we are sort of in the standardized test week here. So first we have the Arrhenius. Okay, so let's get over there. If you don't have it out, grab your book, pause me and get your book. 296, we'll talk you through what we've got here. Okay, these are the kind of things that when I'm underlining them, you need to be paying attention. Okay, you guys, I see a lot of missed things on quizzes that I know I specifically underlined in my book because I still got my book and the stuff's underlined. So if I'm underlining it, you need to know it. Okay, you can put the video on 2 times speed and get through it very quickly, but you should be able to see what I've got underlined in the book. Okay, all right. So, an Arrhenius acid is a substance that increases the concentration of hydrogen ions in aqueous solution. Okay, and then the flip of that is an Arrhenius base is a substance that increases the concentration of hydroxide ions in aqueous solution. Okay, so what's that mean? First of all, we need to remember that the hydroxide is the OH minus. Okay. All right, and before we get to an example here, he starts using some words that are good to know and shouldn't be too hard to memorize. Monoprotic. Okay, so remember that a proton, all right, so we have a hydrogen, right? And what's that look like? We've got one proton in the middle, and even though it's inaccurate, it's going to help us remember. And we've got one electron, orbiting. We know it's not orbiting, but you get what I'm saying. It's hanging out with that proton in the middle. Okay, so that's an electrically neutral hydrogen. Well, if this guy goes away, that just leaves us a proton. Okay, and it's weird to think of hydrogen, which has properties and is an element. You take away its electron and it's just a naked proton, which we sort of think, or at least I think of, as sort of like a basic building block without any properties of its own. But that's what we get. We get it's just a naked proton. Okay, so if we've got an H and a Cl, and this goes to an H plus and a Cl minus, well, this is just a proton then. Okay, that's what we got going on there. All right. So if we do just one of those, like in HCl, that's monoprotic, 1. And then if we've got something like an H2SO4, what happens? It goes to an SO4 2 minus and 2 H plus. Okay, so it's diprotic. Pretty straightforward. And then even some go H3PO4, and they break all of them up, and they're triprotic. Okay? All right, and so what do we see here? He gives us an example. We've got a strong acid here that completely disassociates. It's a strong electrolyte. We have hydrogen chloride or hydrochloric acid when it's aqueous. Breaks up completely into every one of them breaks up into an H plus, or just about every one of them, H plus and a Cl minus. So that's increasing the hydrogen concentration in a solution. Okay. All right, and so that makes that one a strong acid, and we see here this guy also goes from acetic acid into an H plus and the acetate ion, both in solution here, and that increases the H plus. But whereas, let's say, for discussion, 100 out of 100 of these ionize, maybe only 1 out of 10,000 of these ionizes. So it's weak. So you put a mole of this in here, you don't get a mole of that in solution. You get almost a mole of this hanging out with 1,000th of a mole, let's say, broken up into this. Okay, so the lucky few ionize, and most of them are left hanging out like this. Okay? All right. So, we also need to be clear, but we're going to clarify a little bit. We said it increases the hydrogen ion, and Crazy Dude in the video mentioned this, but you probably were a little bit lost at that point. He talks very quickly, although pretty clearly. All right, so if we put these things together as a liquid and H2O as a liquid, that becomes what we get. So this hydrogen migrates over to here, and we end up with an H3O plus and an NO3 minus. Okay, so whereas we might have written this doesn't happen. They actually get together and form this. Okay, because that water is polar, remember, we've got H, O, H, and this has got that little partial negative and partial positive here. That other hydrogen, this guy, comes over here because he's a positive, comes over and starts hanging out close enough that it's considered a bond. Okay, and so that makes it an H3O plus, and what do we call that? That's hydronium. Okay, so you need to know that. Okay, you need to know that that's what a hydronium ion is. You will be asked that. Okay, so now more clearly, an Arrhenius acid is a substance that increases the concentration of hydronium ions in solution. Okay, so it's essentially the same thing, except that instead of saying H plus, we see that H plus joins up with the water and it becomes H3O plus. Okay, nothing crazy here. That's pretty much the extent of what we'll need to know there. Okay, so you need to know that definition. Okay, so why do we have more than one definition? Well, let's look right here. Okay, Arrhenius gave us a good starting place for defining acids and bases, but it gradually became apparent that there are many cases his definitions don't address, primarily because they were articulated in terms of ions in aqueous solution. Many acid-base reactions can occur apart from aqueous solutions, which specifically means water, right? So you might be doing something in another type of solution that didn't involve water. And he gives an example of hydrogen chloride and ammonia can react as gases to produce solid particles, which seems crazy to me. I'd like to see that. He has a picture, I think, somewhere, but I wasn't able to see that. I'd like to look that up and find that. So, you know, if you're doing chemistry for your life, you're going to experience a whole lot of stuff that you and I are never going to really be around. So when they say many cases, they're not cases like you run into when you're cleaning your sink and something happens, or you're like, you know, cooking food and something happens. This is like industrial stuff, and inorganic chemistry and professional chemists are running into these things. So as he says, in this reaction, the acetic acid molecule donates a proton, but the reaction cannot be described in terms of Arrhenius model because the proton doesn't form hydronium. Okay, it's transferred to the ammonia molecule to form ammonium. All right. So, and you can see that. You can look at that and pause and sort of look through that and see where the hydrogen's going to and coming from and all that. All right. So what they want to do is, whereas this might be what Arrhenius can describe, this, including that, is what Bronsted-Lowry can describe. Right? So they're not opposed to one another. This guy is more inclusive than this guy is, okay? All right, so let's get some definitions here. Bronsted-Lowry acid is a proton donor. Okay, so where we were talking about forming hydronium ions, if we don't have the water, we just talk about it giving up that proton. So HCl still is an acid in that sense. Okay, and a Bronsted-Lowry base is a proton acceptor. Okay, so if we look at this particular one, what do we have? This guy goes from this to this, so he's donated a proton, so he's the acid. And this guy goes from this to this, and he has accepted the proton. He had 3, and now he's got 4 hydrogens, so he's the base. Okay? Now, okay. All right, so let's look what happens in another case right here. Let's see if I can get this a little less shiny for you. My book's in the way here, and I'm having trouble getting it to be where I need it to be. Okay, here we go. All right. So, but what happens now that they've formed this? Well, now this guy could definitely be a proton donor, right? He's got an extra proton, and he might give it up to just become water again, right? Okay, so when you have an acid donates its proton, and see that is now lost, it's just an NO3, it becomes a Bronsted-Lowry base. Okay? And just don't try to get confused with any of this. Just roll with it. The acid becomes the conjugate base, all right? And the base becomes the conjugate acid. All right? This always confused me, and it was until I went through chemistry the second or third time that I kind of started to understand it. So the proton is donated, and then, of course, once it's in this form, it can accept a proton, which means it's a base according to our definition here. Okay, and then the base becomes a conjugate acid. Okay, so you will need to be able to label something like this. How about we say be able to label? Ah, little poet, didn't know it. Okay, and I don't think he says it, but usually when it's a strong acid, it forms a weak conjugate base, and if it's a strong base, it forms a weak conjugate acid. And I believe vice versa. If it's a weak acid, it forms a strong conjugate base, just based on how much those things want to go in a particular direction. Okay, well, we won't belabor that point anymore. Okay, and you just basically you just need to check things according to these. Did it donate a proton? It's an acid. Did it accept a proton? It's a base. Like, don't try to get into whether it seems like it should be a base or not. Just ask that question. Did it donate a proton? It's an acid. Did it accept a proton? It's a base. And I think for right now, that's all we want to say about those. So you've got a clear definition. One increases the hydronium, and one increases the hydroxide under Arrhenius. And then one donates a proton and one accepts a proton under Bronsted-Lowry. And then finally we have the last one with Lewis. Okay. And a Lewis acid is any species that accepts an electron pair to form a covalent bond. And a base is any species that donates an electron pair to form a covalent bond. So, accepts an electron pair or donates an electron pair, okay, as an acid or a base. Now, I will not lie to you and tell you that I understand why all of these different definitions exist, or how I would even tell what the difference in those is, which is why I'm going to leave it there and just ask you guys to know those definitions. Okay, because the rest of our time is going to be a much more mathy and less definitional thing. And so we've got the strengths of acids and bases here. Okay, and they're just ordering these. Okay, so not very much. Ionizes down here, and everything ionizes up here, and there are different constants all along here, going from very, very, very small, sorry you couldn't see my pen there, very, very, very small to 100% up here. Okay, and then I was right. Okay, here we go. I forgot about that. Yep. So notice that this is the acid and this is the conjugate base. This is it with the proton. This is after it's donated the proton. Note, very strong acid, extremely weak base. Very weak acid, very strong base. Okay? And basically that kind of makes sense, right? Like, if this ionizes completely in water, it wants to be split up as an H plus and a Cl minus. So if you have that base floating around, it's not just going to accept an H very easily. If it wanted to accept an H, it would have never left the compound HCl in the first place. Okay, so there's something about those atoms or those polyatomic ions that make them want to ionize one way or stay in their compound, as the case may be. Okay, so you just need to know that a strong acid forms a weak conjugate base, and you got some kind of right in here that, like, it's a weak acid, and when it donates, it's a weak base. Okay, and weak is not talking about functional. It's not talking about good or bad. It's just talking about how much of it ionizes, how much of it comes apart into pieces, and we could think of it as about 50% of it may come apart right here, just to get it in the right ballpark in our mind here. Okay, well you can read through here what's going on. I said I wanted to keep it down to 20 minutes, and we're already over that. So I will post some homework for you guys to do from 11.2, and that'll get you a little bit familiar with some of those. and then we get to go into the little bit math section here. But again, nothing. Don't get overwhelmed with that. It's very basic multiplication, and then some of the log stuff, which is really cool and is going to get you really familiar with using all that stuff. Okay, but we'll pick that up on Tuesday, and you guys will have plenty of time to get to work on that. All right, y'all have a great rest of the week, and I hope this is Thursday when you're watching this, and you're knocking out your chemistry homework. All righty, I'll see y'all later. Thanks.